I will just call this a transition. Yeah, so this describes the interaction. Yeah, so the most important example is that you have a unitary U in A tensor C, which is just a discrete moment for a quantum Schrödinger, the dynamics of a quantum system, yeah, of the combined system. Yeah, that's the unitary U, and in this case, the interaction, this transition would be J of A U star A tensor 1 U. So you see this notion of transition, it concentrates on the observables of the system A. And look what happens to them when the interaction takes place. So, as I said, you want to study interaction of A with a whole sequence of copies of the system C. Yeah? So C1, C2, C3, and so on. And if we do that again and again with different copies, then after n steps we have the following. We have Jn from A to A tensor product of C1, C2, and up to Cn. And Jn is just a product of these interactions, J1 times G2 up to J bracket n. Yeah? And the Ji in brackets is just a copy of the original J, only acting on A and Ci and identity everything else, everywhere else. Huh? So you see it's the Heisenberg picture. So it first interacts with system 1, then it interacts with system 2, and so on until system n. So that's what we have after n steps. Huh? For example, and that's what we'll see later, we can think of a sequence of atoms interacting with an electromagnetic field in Micromaser experiments. We'll come to that. Okay, so yeah, so we consider the transition, this interaction, as fixed. That's something which is given by the experiment. And now we want, by arranging these systems Ci in a suitable way, influence the system A in a way we want. Yeah? So you see this produces questions of a control theoretic flavor. Yeah? Right, and let's make this precise. We look at states. So let sigma and rho be normal states of A. And we say that rho is J preparable from sigma. So J is this transition coming from the interaction between A and C. If there exists some subset of the, some subsequence of the natural numbers, and states theta k on the corresponding tensor products Ci from 1 to nk, such that sigma tensor theta k after j and k applied to A converges to rho of A for all A in A. So let's think about it and see what this is really what we want. So that says that if we are able to prepare these states theta k in these finitely many copies of the Ci's, then we just have to run the interaction nk times, and then the original state sigma is transformed to rho by that. Yeah? So just by doing the interaction j nk times, we have transformed the state sigma to the state rho. That's what it says. Further, we say that rho is universally J preparable if we can find such theta k which work simultaneously for all initial states sigma. So this is, I add here, this is a very attractive situation, because in this case we don't need to know the initial states, and we're still able to repair rho. That's a very attractive situation. Yeah? So you don't know what the initial state of A is, but if you choose the nk in a sufficient way and let the interaction take place nk times, then you know you are close to rho. Yeah? So you also see that.
Does the system nk depend on your rho, or not necessarily? Would the sequence nk depend on your rho, or not necessarily?
In the universal case, you mean, or? Yeah, in the first case, it certainly depends on rho exactly. That's what you need. You want to have rho, and you choose the theta k accordingly to get rho. Yeah? Exactly. Yeah. So this is what you can choose. You should think that you have that you cannot directly influence the system A, but you can prepare these systems C. So you are able to prepare these theta k's, and by using the interaction, you change what you have in the system A. That's the idea. Yeah. Okay. Yeah, and you see it's approximately, but if you do it often. If you do it sufficiently often, then you get as close as you want. So that's exactly what an experimentalist want. I think you can do it with any precision you want to have. All right, so that's the problem. To do that, yeah. So this universal preparability that you can prepare a state without even knowing where you start from, that first state might look too good to be true, but the following argument shows that it's actually not so uncommon. Suppose that your transition is of the form alpha, A goes to alpha of A tensor 1 with some star automorphism of A tensor C. Then we have a time-reversed version, JR, which maps A to the minus 1 of A tensor 1. For example, in the case where J is U star A tensor 1 U, that's clearly possible. And in this case, you can prove the following. Say your A is B of H, and J is from B of H to B of H tensor C. If there exists a vector state, omega psi, which is both J and JR universally preparable, then all normal states are universally J preparable. And let me give you the intuition. It was the wrong directions. Sorry. Here's the main idea. So we suppose you want to prepare the state rho. Then check that if a vector state omega xi is JR preparable from rho, then conversely rho is J preparable from omega xi. That's yeah, you have to do something to prove that, but it's maybe plausible. Yeah? But given that, it's easy. Yeah? Now, if you have an arbitrary initial state, you can first use the universal J preparability to prepare the omega xi. And then, using the argument before, with the universal JR preparability, you prepare the rho from that. Yeah? So you do it in two steps, taking this vector state as an intermediate. As an intermediate. Yeah? So it's a relatively plausible theorem, and you can already do some nice examples with that. Yeah? Example I call the generalized Micromaser. Say A is a bounded operators on L on an L2 of n, or n0. Think of it as one mode of an electromagnetic field. And C is just a two-level atom, so it's 2 by 2 matrices. We denote the basis as 0, 1, 2, 3 for A and just 0, 1 for C. And our transition is just A goes to U star A tensor 1 U, with U as follows. Maybe I should enter the next one. This is something which can be obtained by the discretization of the Jaynes-Cummings model in quantum optics. And we call this a generalized micromaser, but by discretization you get specific coefficients. And what happens? Well, you should think of this basis, of these entries in the basis as the energy which is there, which is present. So if you have no energy in the field and in the atoms, then nothing happens. So U of 0, 0 is 0, 0 is an invariant vector. And if you have n minus 1 quanta in the field and excited states in the atom, it can stay like that, or this one quantum can be exchanged. Huh? And the other way around, if you have n quanta of energy in the field and the ground state in the atom, one of these energy quantum may be exchanged, and you have some coefficients then, alpha and beta, beta plus, alpha plus. And what you need to make this a unitary is that you have unitary 2 by 2 matrices like that. Yeah? So you have a one-dimensional invariant space and many two-dimensional spaces which are left invariant by that. Yeah? So that's a discretized version of a Jaynes-Cummings model. Yeah? And interpretation is just that one quantum of energy is exchanged in each step with probability modulus beta n squared. And the alpha modulus squared is that everything stays where it is. Yeah? So that's something that can be done in Micromaser experiments, and we can prove that, in fact, in the generalized Micromaser, all normal states are universally J-repairable if for all n greater or equal 1, the beta n are not 0. That physicists' terminology is there are no trapping states. And that's obviously a necessary condition, because if beta n is 0, it means that you cannot go from n minus 1 level to the n level. And then it's, of course, not possible to prepare something. If you start below, you cannot prepare something which is above it. So it's a necessary condition, but it's also sufficient. Yeah. And the idea of proof is that we can apply the previous result for the ground state of the field, 0. Yeah, yeah, so remember what we need, that it's both J and JR universally repairable. And it's intuitively very plausible and can be checked also rigorously that this ground state is J and JR universally repairable just by interacting with sufficiently many atoms in the ground state. Yeah, if you send in a lot of atoms in the ground state, then it takes out more and more energy from the field, and in the end you are in the ground state. Yeah? So that's what you would expect, and physicists used this idea before we had this rigorous proof here. Yeah. Simulations seem to indicate that this procedure often is also the most efficient one. So going to the ground state first, and from this ground state, then again prepare what you want. Yeah? I'm not aware of any rigorous proofs of this efficiency considerations. So that may be an interesting thing to study. Okay. Yeah, so let's come to the general question. General question, which interactions provide universal preparability of states? What is that's the question, yeah? It's a property of the interaction, and you want to find out what it is. So, and let's study the setting of noncommutative Markov processes, namely the following one, which is a traditional setting in quantum probability. So suppose there are faithful normal states phi of A and psi of C, such that phi tensor psi after J is phi. That's a kind of stationarity assumption. We can think of this as a stationary noncommutative Markov process. The easiest way to see what's Markov here is to think of the operator T psi equal to P psi after J. So J goes from A to A tensor C, and P psi is just a conditional expectation which you get by evaluating the state psi on C. Yeah? So that's a transition operator of a noncommutative Markov process. And in fact, if you ask why this is Markov, one of the things you can see directly is that if you take the Jn, the n times repeated interaction, and then evaluate the tensor product of the psi's, you get the nth power of T psi. And this is the typical semigroup property of the transition operator of a Markov process. So that's my explanation why you should think of this as a Markov process. And the condition we have translates into the fact that this phi is invariant for T psi. So we have a stationary faithful normal state. That's our assumption for the transition operator. Okay, so for stationary Markov processes in this sense, around 2000, Kümmerer and Maaßen introduced the scattering theory for noncommutative Markov processes. And I just let me just give you the idea of asymptotic completeness of this scattering theory. Some equivalent conditions which characterize that. So 1, J is asymptotically complete. 2 is the reason why it's called asymptotically complete. Namely, the assertion is that you have an isomorphism of phenomenal algebras, A tensor, infinite tensor product of C's, always for Neumann tensor products, which we have here, to the infinite tensor product of C's, which intertwines the dynamics on the left algebra, which is induced by J, and the tensor shift on the right. Yeah? So you should think of the tensor shift on the right as a kind of pure dynamics, and the J is then some kind of perturbation. And if this is conjugate to each other, you have a kind of asymptotic completeness. Yeah? So this isomorphism is the Miller operator in this scattering theory. Yeah? Okay, you can study when this is possible, and a bit more concrete condition, which is equivalent, is stated as number 3, it says that Jn of A, that the difference between Jn of A and Qn of Jn of A, where Qn is just the conditional expectation you get by evaluating the state phi on A. Yeah? So, and if n goes to infinity, that's the limit here, then this norm becomes small. It's the norm which is built from these states. The Hilbert space norm you can build from the states. All right. Yeah? So it's all a bit technical. But there's an intuitive way to think about this last condition here. It says that asymptotically you have something like 1 tensor Cn. Yeah? So this gives you the connection to the preparability we studied earlier. Yeah? So roughly asymptotic completeness means that we are in the Heisenberg picture. Look at the observables in A, which we think of embedded as A tensor 1 in the big algebra. And asymptotic completeness says that asymptotically this is transformed into something of the form 1 tensor something, yeah? 1 tensor, call it C infinity, something in this infinite tensor product of the C's. Yeah? So that's asymptotic completeness. But let's look at this in the Schrödinger picture and think of the original state is sigma tensor psi infinity. Yeah? So sigma on the system A and something on these copies of C. Then what happens asymptotically? We start with for this observable A in A. Asymptotically, it's of the form 1 tensor C infinity. Yeah? But if you then evaluate sigma tensor psi infinity on that, you see it's just pi infinity of C infinity. So it doesn't depend anymore on sigma. Yeah? That's exactly what we wanted for universal preparability. Yeah? It doesn't depend anymore on sigma, and if you are free to choose the psi infinity as you want, you can get everything you want. Yeah? So the intuition tells us we should be able to get universal preparability for all normal states from asymptotic completeness. And modulo technicalities, this is true. Yeah? So we have the following theorem. It's for A equal to B of H. The transition goes from B of H to B of H tensor C. And suppose there exist faithful normal states phi on B of H and psi on C to be in the setting we studied. So we have a stationary Markov process in this sense. The following are equivalent. The J is asymptotically complete. The other statement is all normal states of B of H are universally J repairable. And technical condition, J is tight. I come back to this later a bit, but I should say here that in many cases this is satisfied automatically. For example, if A is B of H, as we have it here, and J of A is alpha of A tensor 1 with an automorphism alpha, which has phi tensor psi as an invariant state, then tightness is automatic. So in this situation, which for example is the case in this generalized Micromaser example, in this case the tightness is automatic, so the fact that all normal states of B of H are universally J repairable is just equivalent to the asymptotic completeness. So, and we can also conclude from that the generalized Micromaser without trapping states is always asymptotically complete. So that's a nice result for this example too. Right, I have something like 15 minutes to go a little bit into some tools how this is done, and I think that that is also interesting. Well, so an interesting technique used in rigorously proving these results is the following purification method. Well, question in brackets, can it be used for solving other problems too? Yeah, but maybe one of you have ideas. So the construction is as follows. We have this non-commutative probability spaces, A with a state phi and C with a state psi. We do GNS construction, and let's call it GNS Hilbert space H, and the cyclic vector psi phi. And in the other case, from C psi, we get K eta psi. Okay, and then we have this transition here, the star homomorphism preserving the states, A phi to A tensor C phi tensor psi. From this, you can easily check that on the GNS level, you get an isometry from H to H tensor K. And now we just use this isometry to build a CP map. We are the usual Stein-Spring formula. If you have any operator in B of H, we can map it, say X, we can map it to V star X tensor 1, X tensor 1 V, and we get a unital completely positive map on all bounded operators on the GNS space. So not just on A, but on all operators of the GNS space. So this CP map set prime, we call the dual extended transition operator. Reason for the name is that it extends the dual transition operator T prime from A prime to A prime on the commutant of the Markov process. But that's not so important for the following. That's just the explanation for the name. Important for us here is that while the original transition operator has the invariant faithful state phi by assumption, then this dual extended transition operator Z prime has an invariant vector state, namely the corresponding cyclic vector psi phi gives you a vector state, and you can check this is invariant for the Z prime. Yeah? And this is a huge advantage in these constructions, because correlations involving a vector states are easier to handle than correlations involving a mixed state. I think this is the main reason why this technique of introducing the Z prime is useful. And we introduced it to deal with asymptotic completeness, and in this case we have in fact a nice result which says that J is asymptotically complete if and only if this Z prime thing is ergodic, has no non-trivial fixed points, or equivalently it's mixing, which means that all the states are transformed into this vector state asymptotically. Yeah? So let me say that a result like this is definitely not true if we replace Z prime by the original transition operator, T phi. Yeah? In fact, transition operators T can have different extensions in this sense. Some are ergodic and some not. So in other words, the original transition operator does not contain all the information about being asymptotically complete or not. that's something of the interaction. It's not in the original transition operator, but it is in Z prime. Yeah? So Z prime contains all this information, which we need to study that. Yeah? And so all the relevant information is in the spectrum of Z prime. And this can clearly be a useful criterion. For example, if A is finite dimensional, then also Z prime is finite dimensional, a finite dimensional object. While all the statements we have seen before about universal preparability and asymptotic completeness, they all involve infinite dimension. Yeah? So this may actually be useful in practice to compute Z prime and see what the spectrum is. Eh? Okay, let's also have a look at the case where A is infinite dimensional. So the system we want to study. That's, for example, in this Micromaser example, we had an infinite dimensional A. Yeah? We had all possible energy levels going to infinity. So in this case, it's necessary to speak about tightness, and substantial part of the paper I mentioned is about technical statements which go towards a theory of tightness. Yes, the null setting allows to develop this notion, so let's study this a bit. So you've seen that in your probability courses. It's a concept from classical probability theory. So the definition is that a family of probability measures on a Borel sigma algebra is tight if for all positive epsilon there's a compact set such that the probability of its complement is at most epsilon for all members of the families simultaneously. Yeah? That's tightness. Yeah, and for discrete spaces, we can talk of finite instead of compact sets, which is in this case the same. Yeah? So in probability, this is an extremely important notion in a technical sense if you want to deal with limits, and we want to study limits. So in fact, recall the well-known theorem of Prokhorov, which says that there are many versions for example, for Polish spaces, tightness is equivalent to weak relative compactness of the family of probability measures. Yeah? So if you want to find some accumulation points and things like that, you should look for tightness. Yeah? And so we needed some non-commutative version here, and what we were able to prove is the following. Yeah. So that's an important technical step to achieve rigorous proofs for our results, and it can be proved that a sequence of normal states on B of H is tight. I have to give you the definition, in the sense that for any positive epsilon, there exists a finite dimensional projection such that the expectations of its complement are all at most epsilon for every member of this sequence. Yeah? Okay, it's tight if and only if this sequence is relatively compact in the norm topology. Yeah? So if you have tightness, you can produce limits. That's the version of Prokhorov in this setting. Yeah, note that B of H is an atomic von Neumann algebra. So we should think of this result as generalizing the classical Prokhorov theorem for discrete spaces. Yeah? So look, we have, instead of finite sets, we have a finite dimensional projection. Yeah? So I'm not aware of a worked out generalization of the Prokhorov theorem for general von Neumann algebras, and I think that's one of the reasons why we state some of our main results for B of H. Yeah? So there's some work to do. Yeah. Yeah. Okay, so this is the tightness for normal states on B of H, and as a postscript I can give you the definition of tightness of a transition, which appeared in one of the theorems, in one of these equivalences. Asymptotic completeness was equivalent to universal preparability for all normal states plus tightness, and it can be. We can define it most easily in terms of this dual transition operator Z prime, and the requirement is that for all normal states, sigma, the sequences sigma composed with powers of Z prime are tight in the sense given. Yeah? And so you see we get some compactness, and you see for asymptotic completeness we need some convergence. So you should assume something like that. And we don't miss anything. It's a necessary condition for asymptotic completeness, because as we have seen, asymptotic completeness is equivalent to Z prime having this absorbing state. It's mixing to this, going to this vector state. And if it's mixing and going to some asymptotic state, it's clear that these sequences are tight, because for big N you can just replace it by the limit. Yeah? So yeah, that defines everything. Okay, it was a bit too quick. I already come to the conclusion. So final remarks. Yeah, I hope to have convinced you that the study of asymptotic completeness and of related criteria is relevant for the development of a control theory for open quantum systems. If you accept that this idea of preparability of states in the open system is a good way to formalize controllability for such a system. Yeah? And second aspect is that the corresponding functional analytic and operator algebraic tools, such as extended transition or the noncommutative Prokhorov theorem, deserve further development. And there are some things which can still be explored. This setting of noncommutative Markov processes with faithful normal invariant states is clearly not the whole story. It's just a nice situation. Yeah? One example of a further development is you cannot only, in control theory, you're not only studying controllability, but also observability. And it's a kind of dual notion. So in our situation, observability can be defined as a property that you can find out about the state of the system A by only looking at the environment, these C systems. So you only measure in these environments, and you want to find out about state of the system A. That would be a reasonable notion of observability. And yeah, so it's a dual thing. So it shouldn't be surprising the result we have, that in the setting of these stationary Markov processes, observability in this sense corresponds to asymptotic completeness of the time-reversed system. So again, asymptotic completeness can play a role in in characterizing the situations where you have observability as well as controllability. Yeah? So we are working on refinements of this observability thing. Yeah? Okay, thank you.
Q? Yes. So that's here.
If you have these input states, theta n,
Yeah.
For n successive operations, and is there a version of this theory where you require these to be separable?
Yeah,
So let's do this step by step.
That's a very good question. Yeah. So in these experiments, which were, for example, done in long ago in Dresden at the MPI, they also did computer simulations which seem to indicate that that often separable states are good enough to get everything. But again, I'm not aware of any rigorous proof for that. Yeah, yeah, that's a very valid point. These theta k's I introduced in these theorems are states on n-fold tensor products. So they can be anything. They can be entangled in a very complicated way, and the things we get in the proofs here, in fact, are. Yeah. So the answer is not clear. Yeah?
Marius?
I have a comment for this preparability in the Schrödinger picture. I think here in this community, this is better known as embezzlement. It's very close to embezzlement.
You think it's close? Huh? Okay.
Yeah, it's very close, because embezzlement also means you start from something arbitrary, you do the right transformation, and you get something even more arbitrary.
Okay.
And it's very close related, just a slightly different approach.
Okay.
And then the other comment I have is this extension to Z prime appears very often in quantum loop channels. So in the quantum loop setting, as
Yeah.
studied by Gohm and Rolf. So that's a very common feature in connection with group and quantum loops.
Yeah. So you say you say if the interaction is done by some co-multiplication or something like that. Huh?
Yeah.
Okay. Yeah.
It's very natural.
I see. Yeah. I see.
So this is starting to sound like some sort of resource theory. We have resource theories of entanglement, resource theories of asymmetry, resource theories of given a set of operations and a set of sort of free states, what can be made. Have you looked at it in that context?
Resources. You mean what you need for the theta k's? These input states.
Yeah.
You mean, yeah? Yeah. As I said, it's. I think as far as rigorous proofs are concerned, almost everything is open here. Yeah. Because what we do in these proofs, which is about existence, is just highly entangled, but we don't know if it can be done easier. Yeah. Yeah, that's also a good question. Obviously. Yeah.
You talked about Maser, so is there something like stimulated emission, or there's a debate in quantum optics to know how you describe stimulated emission, many photons, because sometimes you cannot put it as tensor products, and there's much debate to know what is the origin.
I'm not sure if I.
Physics is more or less.
I'm not sure. So.
What is the statistics of this kind of process, like a Maser?
So we have, of course, a very simple model. We just have these tensor products. Yeah? So.
Because when you have a Maser, you have this phase transition. Well, you have many special things.
Yeah, I'm not sure.
That's why they call it a Micromaser. It's not really a Maser.
Yeah. So of course the the concept of non-commutative Markov processes is also more general than just these tensor products. So you can do more complicated things if you want. Eh?
Do you have any more questions? Okay, if not, then thank you again.